Thank you, Paul, and very much thank you for inviting me to talk here. It's a nice topic, and so my name is Juha Tiihonen from Tampere University, but the topic of today dates back a few years when I was with QMCPACK team working as a postdoc in Oak Ridge. So that's why I want to acknowledge Jaron Krogel and Paul Kent for also having major impacts in the development of this method. So STALK, I want to start with a kind of lighter step. Generally speaking, how do you stalk? You locate prey, you follow their moves, and you keep the noise down. It's quite simple, really. How this relates, I'll explain in a bit, but first, to outline this talk, I would like to refer back to the QMCPACK workshop 2023. There was the same topic covered in a lecture by Jaron, which has great background, in my opinion, on the physical origins and the kind of applied intrigue and impact of this capability of doing geometry optimization with DMC. So really watch that. For the background, I will take on more kind of hands-on focus for today. But first, I will give some background on the geometry relaxation and then outline the theory of this method called surrogate Hessian accelerated parallel line search. And finally, if I have the time, I'll walk you through how to use STALK for your own Hello World geometry relaxation project. So how do you predict geometries from first principles? Well, I guess the philosophy of first principles is that we're trying to get by with as few empirical parameters as possible, do predictions from theory only, and in the scope of this workshop, this means solving the Schrodinger equation, well, maybe at 0 Kelvin in Born-Oppenheimer approximation. This is a reference to Paul's introduction slide. And in the Hamiltonian, I like to draw the focus to these variables, which I denote by capital R, which are the ionic coordinates, point-like particles in the Hamiltonian that contain the atomic structure that we're treating. And the formalism, or the kind of the task of predicting the geometry is to find the position that minimized the ground state energy. Now, if we allow some elimination of symmetry, this degree of variables boils down to something that we call the potential energy surface. And in one dimension, such as the binding curve of a dimer, we can see that when we're making different formulations of the theory or different approximations to the Schrodinger equation, we get different potential energy surfaces out. So the Hartree-Fock surface is obviously different from VMC and DMC, and therefore each predicted geometry, that is the minimum of energy, is also different, if only slightly. This also applies to the degree where the minute details of the QMC methodology, for instance, such as using different nodal surfaces or different pseudopotentials or spin orbit effects or whatnot, they also span a different potential energy surface. And I know I'm being painfully explicit here, but the point is that if we want to make fully self-consistently first principles thinking and prediction of geometry, or any other observable for that matter, we should or ought to use the consistent geometry for DMC, that's the DMC geometry, and so on and so forth. And that was a good example of the effect that the structure may have by in the lecture by Hyundak last week on a germanium selenide. I have an example of my own too, which is the chromium triiodide monolayer. It's a structure that boils down to 3 parameters, one of which is the lattice constant, and then there's 2 atomic distances, and the rest is symmetry or crystal structure. Now, if we take slices through the PS along changes in 2 of these parameters, we see that in the dotted line there's a DFT PS, which gives the minimum of energy in some value, and then there's DMC, which gives another value for both of these parameters actually. And if we just, for analysis, expand this PS slice to the second order in the parameter displacement, we notice that indeed the energy minimizing parameter value P star differs by some 3%. However, the shape, the harmonic coefficient in this expansion stays roughly the same between those 2. So we can assert the DFT holds some transferable information of the PS that we can and we will exploit in performing the DMC energy minimization. Before going to that, I will just kind of in a hands-wavy way illustrate the challenge of a noisy PS minimization. So, well, we are trying to locate the minimum of energy. So if the PS is smooth, it's quite easy to imagine different algorithms for finding the zero of force, that is the zero of energy gradient. And this is indeed what basically all DFT codes and other deterministic codes do. It's a push button approach, minimize the force and you find the energy minimum. But now, in contrast, if the PS is noisy upon evaluation, we have only finite number of samples to spare. So each subsequent PS evaluation has a discontinuity in between. It's suffice to say, minimization of the PS is complicated. There's a lot to say about this, but I'll just skip through and mention briefly that there are QMC force estimators, and there have been quite a while actually, and impressive science has been done based on them. And to be honest, forces are the most straightforward and kind of simple way to do geometry optimization. It's just the force estimators, they face a few challenges, and therefore it is kind of intriguing to try out the energy minimization without having to deal with them, and instead focus on the PS, which is the most robust QMC observable, I think. So that led us to develop the surrogate line search algorithm, which was published a few years ago, and it's an energy-based algorithm for relaxation, a cost function, energy, whatever. And actually, it can be used in any stochastic formulation. I call it practical in the sense that its spirit is performance over elegance. We just get the job done. And like I said, it can be used on VMC, DMC. In principle, if QMC, SIPC, I haven't tried it, but I guess it should be possible. Anything with a reasonable surrogate. And I'll get back to the concept of surrogate in a bit. But I want to mention too that actually the contemporary quantum computers would also be candidates for using this algorithm and have been too, as you can see in this archive paper if you look it up. The algorithm itself, outlined on the right, is not overly complicated. It leans quite a lot on the surrogate. And in the end, there's just very simple, conceptually simple line search using the DMC PS or any other stochastic PS. So I'll then kind of go through some practicalities in the details of this method, and it boils really down to optimizing the optimization. And there's a bunch of different issues that we have to tackle, or kind of questions that we may use to exploit or to get better efficiency. Like what is the least amount of information that we need to represent the equilibrium geometry? Or what is the most efficient way to crawl through the PES towards the minimum? How can we ensure that we converge? Also, how do we control systematic and statistical accuracy of the result? Or how we control statistical and computational cost of the workflow and not let it blow up on us? Finally, how do we exploit parallelism and supercomputing facilities in the best possible way while doing this? And these are probably, some of these questions are not very familiar for people doing electronic structure. So I guess I have to kind of warn you that there's a lot of new concepts coming up and I only have so much time. So I recommend that you refer back to these slides when maybe doing exercises or trying out this method to better understand what's going on. Anyway, to treat the first question, what is the least amount of information needed? Obviously, if we're minimizing a structure, we are not necessarily minimizing all 3n ionic coordinate positions. Somehow that's redundant. There's rotation and translation, and maybe other symmetries involved in the ground state that we want to eliminate. And we do this by mapping this R vector to a reduced set of parameters denoted with P. So for instance, this water molecule can map from 9 parameters that are ionic Cartesian coordinates to just 2 positions, which are the angle and the bond length, or it could be something else too, but that's the degree of freedom that we want to optimize. Now, how to optimize these 2 degrees of freedom? Well, we can kind of assume that near the equilibrium P star, the PS can be expanded to the second order through the Hessian HP. And we can, by diagonalization of this Hessian, if we have information of it, formulate this into an algorithm that operates on independent line searches that are based on the eigenvectors of this Hessian, so that we can, in this harmonic regime of the PS, immediately find the minimum by independently searching or minimizing energy along these directions. And you can try it out. Actually, it's in the repository. An example: if you devise a PS such as given on the right-hand side bottom, you can see that if we take a displaced position such as on the top right corner and use the conjugate directions given in red to minimize the energy, both directions individually, we immediately, from any position, we find the minimum. Whereas if we use the original directions in black, we, in the worst case scenario, get a very oscillatory and slow convergence to the minimum. So that's why it's very important to have the Hessian at hand. So the line search seems to be the kind of basic building block of this algorithm. What does it mean? And what are the kind of practical issues with it? Consider that we have a potential energy surface, such as given in the black line on the left. It's the Morse potential, but we only have access to it through a grid of points, a finite number of points, such as the blue or the orange set of points. If we fit, without knowing the underlying shape, some functional form to it, such as the harmonic second order polynomial fit, and find its minimum, we find that, okay, we find the minimum not quite, but we get close to it. And the wider the grid that we have is, the further away from the minimum we get, and that is the fitting bias that comes from the inconsistency between the actual PES and the fitting form. And as we can see on the right-hand side, the bias actually grows systematically the wider we make the line search grid. That's denoted by the grid extent R. Of course, if we make the fit higher order, such as the cubic or quartic, the bias grows slower. Still, it is there because it's not the actual exact shape of the PS. So the wider the grid, the bigger the bias, generally speaking. The other part that we have to treat is noise. So when evaluating a noisy PES, we always get a finite uncertainty of the energy values. They are kind of given in with the blue error bars in the left top plot here, and these black curves here represent different resamplings of the fit based on resampling of the energies obeying these error bars. And so you can imagine that estimating the minimum also has a distribution of different values, and this distribution, or its deviation from the true minimum, can be made into, well, let's say an histogram, where we define that the value of fitting error, of fitting deviation that contains, let's say, 95% of all the results is our estimate of the uncertainty. You can do it in different ways, but anyway, there has to be a measure of uncertainty when there's noise. And the way this scales is that if we make the grid extent higher, so we go further up in the energy, it actually kind of minimizes or it mitigates the propagation of error from the fit, the statistical error from the fit to the minimum finding. Of course, the higher we make the input noise, the sigma, the higher the error bar too. Also, the more we have degrees of freedom, the bigger the propagation of error is. So the harmonic fit n equals 2 has the lowest error bars. And therefore, for this reason, really, we don't want to use too sophisticated or too kind of too many degrees of freedom in the fit. And to summarize these two effects, and by defining that the total error of the fit is the bias plus the statistical error bar, we know that there are competing effects there. And in addition, if we want to impose a tolerance, so we want the total error to be lower than some value, then we have kind of an auxiliary optimization problem. So there's a lot of information here. Let's say we ditch R as the grid extent and instead use W for window. These are variable names used in the code, so that's why I stick to them. Anyway, we know, let's recap that the bias scales up with the window that is the wider the grid. The error bar scales down with the window, and the statistical cost, which was not defined anywhere here, but it's really just the number of samples required. We know by now that it scales down with the variance, inverse variance. So we know that if we want to minimize the statistical cost, we should find the biggest sigma that we can tolerate. So if we can have information of the bias and the propagation of noise, we can construct this map of the grid window versus input noise. And from this map, we can kind of request that, okay, we want to resolve this line search with accuracy of some amount. This means that we can, if we take this window and this noise, we can still be on the safe side, and this is the maximum noise we can allow, and that's the cheapest for us to evaluate. If we double the tolerance for error, we also get can tolerate higher noise and use higher windows. Generally speaking, we know that the optimum noise tolerated grows with the error tolerance. So if we want to have if we don't need to have a very high tolerance for error, a very low tolerance for error, we can save a lot of statistical cost here. And this is why we want to do this. We want to kind of prepare ourselves to evaluate these line searches as cost efficiently as possible. Now, this is only in one dimension, and generalization of this to multiple dimensions, which are in some sense mixed through the Hessian. It's a bit more technical and difficult, and that's handled by the code, but I'm not going to cover it here. So now we get back to the parallel line search iteration, and I want to emphasize that it's parallel in the sense that, okay, this is the point where we do all these independent line searches of the conjugate directions, and since they are independent, they can be searched as at once. And even better, we can ideally assume that they converge in just a single iteration that contains all the directions. So you can basically see this on this figure from the original method paper, where we optimized 19 parameters of the cornene molecule. And as iterations go, they immediately converge to the error bars of to the predefined uncertainties and stay there. And staying in this area is kind of our criterion for convergence, because we don't have access to any other means of validation. This is the best we can do anyway to solve this problem. On the side of the laying out this computational problem, since all the points of a parallel line source can be evaluated in parallel, this means that it's very practical to do this on supercomputers. We don't have to wait for any individual line search. We can do them all at once and reduce the wall time if we just have the resources. And generally speaking, the algorithm goes so that we have an initial prediction for the equilibrium, then we expand it to all these conjugate directions, evaluate the points, resolve the line searches, and there, by doing so, we get a new structure, which we then feed in and start over and repeat until converged. So overall, the steps of the algorithm are such that we use the surrogate method to first relax to a very precise equilibrium within this surrogate PS. We then use this point along the PS, in the PS, to expand or get the Hessian, and from the Hessian we get the conjugate directions, and we characterize the PS along those directions to know how much the bias and the noise, how they behave. And this allows us to optimize the line searches so that we have all the information that we want to utilize in the actual costly, noisy line search, which we then just keep repeating. And what is now this noisy line search based on? Well, the noisy PS can be any stochastic formulation, and typically, if it's a stochastic formulation, it's expensive to evaluate in some sense. It's noisy, obviously. It has high accuracy, because why do it otherwise? We don't have a validation which is saturate. This is what we are after anyway, and the DMC is a perfect candidate for this. The surrogate, that's kind of a cheaper approximation of the noisy PS. So it's then obviously cheap. It's noiseless. It has modest accuracy. I'm not saying it has to be poor. It's good if it's good, but we want to go further. It's self-validating in the way that we have access to the forces and that way of minimization. So DFT works very well. It's already kind of familiar in the QMC ecosystem. Now the question is, how good approximation must the surrogate be in order for this to work? And that's kind of an open problem. It's hard to say how much really is the effect, but ideally and in principle, the goodness of the approximation only affects the efficiency of the workflow, not the outcome. So we'll get to the bottom anyway. To the bottom, by that I mean the energy minimum. All right. Now, back to this introduction. How do we stalk in capital letters? Well, first we use a noiseless surrogate, and second we follow conjugate directions, and third we use them to locate noisy energy minimum. So it's kind of inverse stalking, if you put it that way, but I recommend that you don't read too much into this analogy. It's just to leave a memory footprint. So let me now introduce the surrogate theory accelerated line search kit STALK. It's a Python implementation of this method that I just outlined. It works for noisy parameter optimization, especially if there's a surrogate available. It's found on GitHub. It's open source. It's also found on the virtual machines. You can install it, the development version from the Git, or then you can get a stable version using a pip installer. There's a bit of documentation online, but it's not much, to be honest. I'll get there eventually. The features I want to highlight, though, are that this package has full Nexus integration, meaning that you can run this workflow basically writing Nexus recipes, and therefore it supports QMCPACK and many other codes that Nexus supports too, but also native Python codes. It's easily customized, which is a kind of positive way of saying that it needs a bit of setup to operate. It's, on the other hand, it's kind of unit tested, but it's also in development, so the edges may be rough at points, but I would be very glad to lend a hand in starting its usage if you face difficulties. So I suppose I have a few moments to talk about setting up a STALK project. This is the way I prefer to lay it out. So reading the bullet list on the left, there's a bunch of scripts there. One contains a directory for pseudopotentials if we are using Nexus. And then there's the params.py, where we define the physical problem. That is the parametric mappings, and how do we compute a PES that responds to ionic coordinates or parameters. Then we have the first step, which is the relaxation using the surrogate method, which then feeds some information to the next step, which is the calculation of the Hessian. The third step is creation and optimization of the surrogate model for the parallel line search. And finally, we feed all this information to the actual line search iteration loop. Dividing this to these different files makes it, in my opinion, easy to dissect and analyze, even branch if you want to do that. Of course, it's very modular. You can do it in different ways. You can put everything in one script and call it push button, or you can make a notebook. Just as a note, if you're facing some strange behavior when changing some parameter along this chain of a workflow, remember to clear intermediate results because they may not be updated automatically. But now, for your first line search project, in the params of the py file, we define the parameter mappings. So we make some assumptions of the atomic structure to be optimized, and then we make the forward mapping, which is from a set of positions, which is really just an array of coordinates, to parameters. So we take out the different, we assume that this to be certain ionic species, and then we compute, let's say, distances between certain atoms and angles, and therefore we have a means to return the reduced parameters as another array. And then we have to write a consistent backward mapping, which takes this particular form of an array and then constructs a positional representation of the same atomic structure, of consistent atomic structure based on these parameters. Now, because this is probably the most awkward part of kind of setting up something, I want to kind of rehearse it by suggesting an alternative mapping. So instead of the angle and bond length, we treat just the x and y displacements of the hydrogens in water molecule. So it's the same thing, but now we just measure the x displacement and y displacement, and the backward mapping basically writes itself. In principle, it doesn't matter how we choose these parameters as long as they are consistent and they span the same degrees of freedom. In practice, some mappings are more practical. For instance, it's easier to write a backward mapping for this parameterization, and it's really an open problem what the good practices are. Now, next we want to define the PES. Then that's really just a function that maps a structure that contains the parametric and the real coordinate mapping, the representation of a structure, and maps it into an energy, an error bar. And here we're using just the PySCF evaluation, whose details are given here. And it's really just this simple. I'm not going into details of these all lines. We do also need a relaxation job on the surrogate level, where we provide a structure and we then relax it using built-in methods such as the optimization, using forces. And then we need to write this to a file and read it, because the I/O is not there's no it's done differently in this mode of operation. About the modes of operation, if we are using Nexus, though, that was native Python really. In Nexus mode, we provide a job generating functions and then a consistent loader. So for instance, here we used to write the energy to a file with adding energy to that, and the loader then loads it afterwards, because PySCF doesn't return the energy like that. The DNC job can be produced like so. So we provide a structure and a few other keyword arguments. This is just a summary, and then we generate the physical system, generate PySCF for orbitals, then convert, then do optimization, and then do DNC. And we return just a list of jobs. And Nexus takes care of the rest. take a better look at it in the examples. Now, the first actual actionable step is the relaxation on the circuit level. I won't read through all these lines here, but basically we're just calling the relax PySCF method that we just defined here, and then read the geometry and print it out. So from our initial guess of the structure, we have moved only a little some direction. So we were very close to start with. Now, this is a bit more interesting. Using this energy minimum, we then expand and get the parameter Hessian using a finite difference method, where we take pairs of parameters to displace and then just obtain the Hessian. And here we can see that these two directions are actually very much mixed up in the energy space. And that stands to reason because they are not very natural for a water molecule. Instead, the natural couplings would be stretching of a bond and and changing, wiggling of the angle. And that's indeed very close to being the optimal directions. Using these directions, we then do the characterization of a surrogate. These are also explained in better detail in the examples. Basically, we're just doing a parallel line search with a known energy minimum, and then we optimize it to some degree of accuracy. For instance, here we supply that we want both the x and y parameters to be resolved with 0.01 absolute error tolerance. We use third order polynomial fit to 7 points. And how it looks is that the direction number 0, the first direction, was mapped originally this far along each direction of offset. And then upon optimization, we get this grid based on these red stars here. And this is the information that we'll supply to the actual line search. The second direction goes the same way. So there's nothing to it. In the interest of time, I won't go through this in high detail, but you can play around and take a look how this works. Finally, we do the line search based on this information. So we import the surrogate model, which contains the minimum geometry equilibrium, the Hessian, and also the optimal line search grids and input noises. And then just to make it more challenging, we shift the structure a bit and then do an actual line search iteration using a different PS. And we propagate the line search 4 times, and this is the result. It basically converges almost at the first time, just almost, because the offset was quite sizable, but then it stays here. This is just, of course, this is not really stochastic. This is just DFT plus noise, but it's a good tool to play around with. Now, for troubleshooting, I recommend that you stay mindful of the actual theory and conventions, so you'll understand what's going on. When you're writing the parametric mappings, make sure that they are really consistent. Be mindful of the conversions of units between different codes, also reasonable tolerances, and the fact that some simulations may not always converge to the right states, runs may fail, and this may cause you some gray hair. If you have trouble still, feel free to report the bugs, ask for help. And take a look at these examples that are provided in the GitHub. There's actually one on DMC. It's a bit heavy on the virtual machine, but if you have a lunch break, then you can use that to run down the error bars. Now, as a summary, the geometry relaxation with QMC is a developing feature. It's a feature of importance in some applications, and using the direct PES minimization instead of forces avoids a lot of difficulties, and it's actually a viable thing to do if we have access to these surrogate accelerations and if we can rely on them, such as the starting structure, optimal social directions, and the error characterization. Now, all this is implemented in STALK, so it saves somebody a lot of trouble not having to do it again. It's kind of an ideally push-button approach for doing the PS minimization with DMC. It supplies some, enables some control over accuracy and statistical cost, and it has the Nexus integration for a lot of convenience and efficiency on supercomputers. And with that, I would like to thank you for your attention.
Thanks very much, Juha. You've got a couple of thumbs up and claps on the Zoom, and the presentation's open for questions. And there is one question I see already. First, a couple of comments. So Juha, first of all, thanks very much for presenting this in the evening from Finland. That's much appreciated. And I'd really encourage everyone to work through the examples. It's very easy to get started. And you can use any combination of methods that are in PySCF or Quantum Espresso supported by Nexus, for example. So you could pick a couple of different DFTs or quantum chemical methods very easily. One thing that occurred to me is that there's already about a half dozen papers using this methodology, and it's also been extended for reaction barriers. So you could sort of chase through that by looking at the citations from the papers, so you can see some examples of the kinds of systems that have been done with this. So now the question, this is from Frank. First of all, thanks for the great talk. A couple of questions regarding the arrows of surrogate DFT method. Is there some error bound, and how do different XC potentials compare? So would, for example, HSE, so hybrid functional, be better than PBE?
Yeah, that's one of the kind of open problems. We haven't characterized what would be the best surrogate out of different DFT options. I guess that's an open problem generally in QMC. There's no best option out there. So I guess the critical parts, or if I'm understanding the question right, that we are not too much mischaracterizing the noise and bias properties, because otherwise we are we have no other means of assessing the accuracy other than those. So if they are not as transferable as we would like, then the kind of error estimation is wrong in that by that amount. But since the surrogates are typically, they're supposedly quite cheap, it's probably a good idea to use as good, as sophisticated surrogate DFT hybrids as possible if you think they are better than less sophisticated ones.
Thanks, Juha. Yeah, I was going to jump in and say, I think the general experience here is that one uses the most accurate surrogate that remains affordable. And of course, if you don't know what is accurate, you just have to pick something. But if there's some existing data for your system, or you've calculated and compared with the experiment, you may have a starting point. This is, of course, the problem with DFT, in that we don't know a priori how accurate it's going to be. But usually there's some data on some related systems that one can use.
Actually, yeah, it occurred to me that you can do this basic sensitivity analysis here too. If you compare different surrogates surrogate based on different DFTs, you can pretty much get a hang of whether or not it makes a difference.
And we've got a second question from Anastasia. Can I use an optimized Jastrow wave function at the DMC step? I think an existing optimized Jastrow wave function at the DMC step, or do you have to start all over again? So I think this is about recycling Jastrow functions.
That's a very good question. Yeah, you can, or can you? It used to be part of the code, a standard feature, but it's been remodeled a few times since then. So I'm not sure if it needs some tweaking
I think you
to
can.
be accomplished. But
You
yeah,
can.
yeah, it's still in principle, it's very much possible, even recommended. So that's a
So
good
there's
idea.
been a few studies. I mean, ultimately, again, this is system dependent, but because the Jastrow function doesn't change the nodes, only affects the efficiency of the simulation, generally you can get away without re-optimizing it, right? Of course, things like the locality error and the time step error are changing a little bit in that case. So if you were to do something that's super sensitive, you should eventually do a full re-optimization again. But I think all the applications so far have probably recycled the Jastrow function. I might be wrong
To
on
a
that.
degree, I think there's been a feature where you can supply kind of an equilibrium Jastrow, and then you re-optimize that from a readily good starting position or point. So it's not, you don't have to do all the work from starting from scratch. But yeah, you can do different things, absolutely.